Okay, so can you see my screen?
Yes,
Yes, sir.
totally.
Okay. As you can see, in last class, we started talking about this stability and dynamics for hybrid power grid. And I think we were discussing this slide. We were discussing the questions. And I think we are done question number 1 and question number 2. Now let's discuss a few more questions. Question 3, everybody read. Let me zoom in much more. Yes. Consider you have a hybrid PV. PV means photovoltaic system and conventional synchronous machine-based power generation system to provide power to some customers. Since the PV can't produce power continuously, you plan to connect a wind generator to be mentioned to the mentioned hybrid system. So is this modified hybrid system now able to supply power continuously to meet the consumer's demand? Explain your answer. So meaning of the context of the question that there are some customers who are being powered by the combination of solar system and conventional synchronous machine. Now, since the PV cannot produce power continuously means at night it is off, and even during daytime when it is fully cloudy, PV is not contributing power. So this means that is the problem. And then in order to handle this situation, you plan to connect a wind generator to that hybrid system. So this means you made synchronous, then PV plus wind. So your thought is that because wind generator, depending on wind speed, can run 24 hours. So that is your viewpoint. So that will compensate that absence of PV during night time and cloudy moment. Now, do you think that is this modified hybrid system now be able to supply power continuously to meet the consumer's demand? So the thing is that it depends on in terms of the power amount, it depends on how much consumers need. So therefore, it is expected that the modified system will be able to meet that amount, for example, 10 megawatt or 15 megawatt. But when we say that can it meet continuously consumers' demand? So consumers not only want the amount or the magnitude of power required, they also want the steady power, constant power, and especially constant voltage and constant frequency. Now, if you see, the structure of that hybrid system, because you are connecting PV and then wind, so they are fluctuating sources. Right? So both PV and wind fluctuating sources. So therefore, connecting wind, it can meet your amount of the demand, magnitude of the demand, but still you might get the fluctuated output power, voltage and frequency. Everything will be fluctuating. So that's why you must need to connect an energy storage system. The energy storage will compensate, will mitigate or suppress those fluctuations. So therefore, the appropriate answer would be yes, this modified hybrid system is now able to supply power, but with the with the energy storage system. This means you need energy storage that will meet the consumer's demand. So everybody, could you follow me?
Yes, Dr. Ali.
Yes, yes, yeah. So therefore, I mean, see that you connect a wind generator. So this looks like it will meet, but still it will provide the fluctuated. This means both PV and wind provide fluctuated. So you have to send the smooth power. That's why energy storage is essential. Okay, so now a few numerical problems. So everybody, you need to be ready with your pen paper. Read the problem first. A 10 kilowatt 74 volt permanent magnet synchronous machine based variable speed wind generator is providing power to the grid through a 3-phase 6-pulse bridge converter, a DC link capacitor of 2 farad, and an inverter. If firing angle of the converter is 0 degree, then calculate the energy storage in the DC link capacitor. So probably you remember that last class we were discussing about the fixed speed and variable speed wind generator, and you notice the diagram of variable speed wind generator. You see, it is permanent magnet synchronous machine based, but because this is variable speed wind generator, it is not directly connected to the grid. It is connected through a three-phase 6-pulse bridge converter. And then there is a DC link capacitor. And then there is an inverter. And you can guess after inverter, there is transformer and finally the grid. So this means between this permanent magnet synchronous machine, there are these components. And if the firing angle converter is 0 degree, meaning that for that rectifier, then calculate the energy storage in the DC capacitor. So therefore, if I draw a brief schematic, and that will help you. So let's take you to that whiteboard for a moment. Okay, so everybody see that, for example, this is that PMSG based wind generator. This is the shaft. This is being driven by wind generator. This is that, let me log it, PMSG, permanent magnet based synchronous generator. And then of course, this is the three-phase system. And that three-phase system is attached to that 6-pulse bridge rectifier. Let me write 6-pulse bridge rectifier. So this component is 6-pulse bridge rectifier. This means that is converting the DC. You remember that last class I was showing you the picture, and then there is a capacitor here, which is called the DC link capacitor. And after capacitor, there will be the inverter circuit. So this is I and B. This is inverter. So again, that will convert into AC. And then with the help of the transformer, that will be connected to the grid. So this point is the grid. Okay. So now we are going back to that problem. So everybody see, so here is that capacitor. This is the capacitor, which is called that DC link capacitor. So this is called DC link capacitor. So therefore, you can easily see that this portion is the AC. So here it is AC, three-phase AC. Then this portion is your DC. So this means you need the conversion from AC to DC, and then again from here DC to AC. Of course, because it is inverter, so it converted into AC and transformer. You can see transformer. Definitely that is AC. Ultimately your grid is AC. So now what happens once current flows, from that three-phase system, A phase, B phase, C phase, and current enters into this converter, which is in this case 6-pulse bridge rectifier. Then it is converted into DC, and because there is a capacitor here, you see, there is a capacitor, and this is DC. So what is the property of capacitor? It will store energy. And that you all know that stored energy by that capacitor is which is half CVDC squared in joule. This is for capacitor, half CVDC squared. So this means you need to know what is the DC voltage here based on the given information in the problem. And then this is the energy storage equation. So that was the question. So if you know what is the capacitor value in farad or millifarad, and if you know what is the DC voltage here, then using this equation, you can calculate the energy storage, which is in joule. And that stored energy actually will be transferred with the help of the inverter to the AC circuit. So this is, the law of conservation of energy. There is some AC power here that is converted into DC power here. This capacitor is holding that voltage, and again power is converted into AC. In that way, they are maintaining the law of conservation of energy. So the benefit is that because here your wind speed was fluctuating, your input is fluctuating, power, voltage, everything is fluctuating here. But because you are converting into DC, so initially you are getting like a pulsating DC, but then because you have a capacitor that is providing the smooth DC, and that DC is converted into a good format of the AC, like sinusoidal AC. So that is the benefit, that you see the power here or power here, but you're connected here, customers are connected here, you want this one. So that's why you need this arrangement. So now you see everybody, you note down this picture or keep it in your mind. So this will be the brief schematic of that problem. So based on this, now go back to that problem. Now read the problem number 4. A 10 kilowatt, 74 volt permanent magnet synchronous machine. This means in the figure leftmost side for the synchronous, these are the rating. Its power capacity is 10 kilowatt and 74 volt. Everybody keep in mind that 74 volt is the RMS value or the effective value. And of course, this is the line voltage, line to line voltage. Whatever the type of the generator is, Y connected, delta connected, it is the line to line voltage by default. And is providing power grid through a 3-phase pulse rectifier and DC link capacitor 2 farad. See, the capacitor value is 2 farad. And then there is inverter. And the firing angle of the converter, meaning that rectifier, 0 degree, alpha value. Then calculate the energy storage in the DC link capacitor. Now, everybody, do you understand? Now, can you solve it?
Yes, Dr. Ali.
Yes, please go ahead.
So what is the answer, Dr. Ali? It's 4.028 kilojoule.
4.28.
4.028 kilojoule. That's what I got.
Okay.
Yeah, I got 4.44.
I got 9.99 kilojoule.
So, what was your VDC?
It is 63.472 volt.
Oh, that is wrong.
Okay.
How is it?
So we just use 3 Vm by pi cos alpha. I mean that formula, right?
But you see that this 74 volt, this is the, as I said just now, this is
That's
effective RMS.
Yeah, I converted that back to the peak one.
Did you multiply by √2?
Yes, I did. Let me check my calculation again.
Yes, can you please check? It looks like the answer should be 10 kilojoule.
Yes, that's what I got.
Yeah, so can you please check, Manoj?
Yeah. The VDC should be
100 volt.
99.935.
Yeah.
Right.
Yep.
Yep.
That I did. So
Yeah,
the
yeah.
answer
My
should
mistake.
be, yeah, do it once again. So how Kamana also got the same result? Because you said that's why she is telling?
No, I'm also checking back, Dr. Ali.
No, I'm just kidding. Yeah. I said that because Manoj also, because you must need to follow him. That's why you said that. I said.
That is not necessary.
Yeah. But from the answer, it looks like so. She also said, okay, no, you got. So come on, did you convert into peak value? Did you multiply by √2?
Yes, Dr. I got the same result now.
Oh, 10 kilojoule? Oh, okay, then fine. Okay. So, Amani, you said you got 10 kilojoule, right?
Yeah, for the first time I got something right here.
Okay. So, I mean, your calculator has been good recently.
I noticed something when we don't have pi. No, we don't. We have pi here in this question. So sometimes when we have pi, the value of pi it will be different. But sometimes I use 3.14.
Okay.
But maybe when you use the calculator,
Oh,
other calculator, yeah, it's different. It will have a different values.
yeah, because after 3.1415, there is at least another 10 digits.
Yes, sir. Yeah.
Yeah, got it.
Dr. Ali, I got like 9.987 kilojoule.
Okay, got it. So therefore, like I calculated like 10 kilojoule.
Yeah, almost, yeah.
Sir, I got 9.95. Is it fine?
9.95.
Yeah.
Is it not going to very close to 10 kilojoule?
10. I'll check again.
Yeah, please. Yeah.
Yes, sir.
No,
Like
actually,
9.
I got here to 10 kilojoules.
Okay, good. Sindhuja,
Yes, Dr. Ali, I got 10 kilojoules.
10 kilojoule. Okay. Yeah. Venkat, did you get close? So what Venkat, what's your VDC value? Is it not very close to 100 volt?
Yeah, yes, sir. It's
Yeah.
98.9.
Okay. Oh, 98. It was not 99 point something.
No.
So maybe, so what is your pi value? How did you do that? So 3.14 or you use the calculator?
Yeah, 3.14.
Okay. I think
So-
that would be a little bit.
Yeah, the DC voltage is around like 9 point something, 9.9 something. We didn't get like exactly 10, that's why.
Okay. Got it. Anyway, so then you said 9.98 or something, the kilojoule.
9.95.
Okay, then you can approximate that about 10.
Yeah, yes.
Okay, therefore everybody now read a new problem, number 5. A 5 megawatt permanent magnet synchronous machine based variable speed wind generator with a 0.9 power factor is providing power to a grid through a 3-phase 6-pulse bridge converter, a DC link capacitor of 2 farad and an inverter to maintain 60 Hz grid frequency. The required energy storage capacity of the DC link is 1 megajoule. If the firing angle of the converter is 60 degrees, then calculate the rated input line current of the converter. So in this case, you see the generator rating is 5 megawatt and power factor value is given, which is 0.95. And then in this case, energy storage capacity is given and firing angle is 60 degrees, then what should be the rated input line current of the converter? So in this case, the question is, just let me take you to that whiteboard for a moment. So in this case, what is the amount of current? That's the question. The same picture, for example, let me. This is IL. So what is the current that is entering into the converter? This IL is the question. And then here the P value was given for the generator, which is I think that 5 megawatt. And then the power factor value was given for the generator. So you see, for the generator, power factor is given and then the power value is given. And here the energy storage value was given, which is 1 megajoule. This thing is given. So then based on this information, and then here the alpha was I think 60 degree for this one. So based on this, what should be the input current that is entering to the converter? So therefore again, so everybody keep this picture in front of you and then go back to that problem. See, read this one. Do you understand, everybody? Everybody, do you understand?
Yes, Dr. Ali.
Yes, sir.
Yes, so please do that. You have to find out the rated input line current of the converter. Converter means in this case rectifier, how much current is entering, and that is the line current.
Is it 1.184 kiloamp?
No, it looks like completely different.
Okay, then I did some mistake then.
Yeah, please keep going. Yeah.
So what is your VDC? It should be 1 kilovolt, right?
VDC, yeah, that's right, on kilovolt.
And the Vmax would be 2.094 kilovolt.
Yeah, Vmax, right, yes.
And VRMS should be 1480.96 volt.
Volt, yeah, that's also right.
And this is the three-phase power, right? 5 megawatt.
Yeah, of course, three-phase power.
Oh, okay. So that should be the line voltage. Okay, I multiplied by 3, so it should be √3.
Yeah.
I got it now. 520.6 divided by 3.
So that, let me write down the answer here. I got like
So it is 2.051 kiloamp.
yeah 2000.83 ampere.
Oh yeah, I got exactly that one. 2051.835.
Ampere, right, yes.
Yeah.
Sorry, it is in ampere. Okay, so everybody, you keep trying. So see this one. The answer should be 2051.83 or 2.05183 kiloampere. And of course, this is RMS value. This number, this ampere is in RMS, effective value.
Line current. Yeah.
So everybody keep trying. Yeah. Is everybody trying?
Yes, Dr. Ali, I got the same value.
You got? Okay.
Yes, Dr. Ali.
Great. Yes. Okay. Kamana, how far are you?
Yeah, I'm done, Dr. Ali. It's
The same.
2.05 kilo ampere.
Oh, you
Yeah.
expressed. Okay, that's fine. Yes. And then Amani.
Yes, Dr. Ali, can you please check the chat? Because I share my result over there. Because I got different number, that's why.
Oh, so you did something in chat. Just a moment.
Yes, Dr. Ali.
Okay, hold on.
Yeah, because I have some background noise, that's why.
Okay. This is your final result, I 7.18.
Yes, Dr. Ali.
You're-
No, completely wrong result.
I
Yeah,
can't see where's my mistake.
BM is wrong. I mean, it should be around 2.094 kilovolt.
So
VM?
VDC is wrong. It is like 100, but it should be 1000 watt.
No, 0,000. VDC is 1,000 there.
Oh,
try
this is the top one is the previous. Oh, okay. I was looking the previous. I'm sorry. VDC, right? Yeah. Okay. And then VM, it should be 2094.
Exactly.
So I want to check your VM first.
I do that.
Yeah. So
She put different value for the theta, cos theta.
Yep.
yeah, cos theta is like, I think 0.95.
Yes.
Okay, Amani, so you keep going. So let me, I think, share the screen. Yeah. Everybody, can you see my screen again?
Yes, sir.
Okay. Yeah. Amani, you keep trying and then look the answer. This, I mean, in ampere or 2.05 kilo ampere.
Okay, I will. I'm still trying.
Yeah, yes, try. Sindhuja, how far are you?
I'm working on it, Dr. Ali.
Okay. Like first find out by using E equal to half CVD square, find out VDC. And then use the DC and AC voltage conversion equation and find out the Vmax, and convert that Vmax into Vrms. And then finally you need to use the equation. This is three-phase power P √3 VL IL cosine theta. Then you will be getting the IL.
Okay, Dr. Ali.
Yes. That should be the steps, procedures.
Okay, Doctor.
Okay. Venkat, so
Yes, sir.
did you get this exact number or different result?
Yeah, I'm working on it.
Okay.
Yeah, I got the same results.
Okay. Amani, did you now get it?
No, Dr. Ali, I'm sorry. I got
So first, did you get the Vmax value 2094.395?
Yes, Dr. Ali. My mistake here, I used cosine. I used the power factor instead of cosine 60. That's why I got that the wrong one.
Oh, okay, okay.
Yeah.
Got it.
So I got
Yeah.
the VM correct,
Okay.
2093.33. Then I got for VL 1480.2.
Okay.
So this is the correct answer for the VL.
Yeah. Then
Okay.
you need to use that P equal to √3 VLIL cosine theta, that equation.
Yeah, okay.
And this time, this cos theta is because this is power factor, that will be that given 0.95 in the second line, beginning of second line.
Oh yeah, this is my mistake. I used the opposite instead of using the power factor.
No. So then that is the next step.
That's my problem. Okay, thank you.
You see, it is, you see this, if the firing angle of the converter is 60 degrees, so therefore for the alpha, firing angle is that alpha. And this 0.95 is the power factor. I mean, this is cosine theta. There is also cosine, but that is cosine alpha. Keep in mind, that is not cosine theta. Cosine theta is the angle between voltage and current, which is called power factor angle. And alpha is the firing angle.
Yes, Dr. Ali, that's my mistake.
Yeah.
Thank you.
Okay. Sindhuja, did you get VM value 2094 or still you are calculating?
Yes, Dr. Ali, I got it.
And then you divide it by √2. So your line voltage, RMS voltage will be 1480.96. You need to divide that by √2.
Okay,
And
Dr. Ali.
that will be your line voltage. Then you need to use P equal to √3 VLIL cosine theta, that three-phase real power equation. And where P value is that 5 megawatt, cosine theta is 0.95 at the second line, beginning of second line. And then you, from there, you find out IL value, line current. That is the answer. That's the question, rated input line current of the converter.
Yeah, okay, Dr. Ali.
Okay. So how many finally did you get this correct result?
Yes, Dr. Ali, I got 2120. Not exactly the same result, because always I have a problem with the value of the of pi. I'm using 3.14 for pi. So I got it's too close to your results. It's 2120.
2120?
Yes, sir.
That is much deviated.
Mm,
It is like 2051, and you said
yeah.
2120. That is too much deviated.
So
So hold on. So your, as you said, your VL value is 1480, right? Point something you said.
yes,
And then did you use the equation P equal to √3 VLIL cosine theta?
yes, Dr. Ali.
So therefore from there you calculate IL.
Yes, Dr. Ali.
And P is 5 megawatt. And the cos theta value is 0.95. So you should not deviate that much then, because 2051, if it is nearby 50 or 49, 40, that is okay. But you said 2120, that is much. This is the current value, current magnitude, too much deviated. So maybe again, so your calculator is or something, I don't know.
Maybe the values when I'm find the square root for 2 or 3, sometimes I need to get more digits. That will give.
Okay.
Usually I take
So
just 1 or 2 digits.
okay, so therefore √3 in this case 1.732, at least you should put that on. √3 is 1.732.
I'm using 1.7.
Oh, no. That is it. 1.732. Minimum. You need to use that number. If you divide with big number at the denominator, 1.732 or something, then your value will be reduced. I mean, close by answer is okay. 2051, 52, or 48, 49. Those are okay because of the rounding issue. But if it is too much deviated, like about what you are telling about 80 ampere, 70 ampere difference, that is too much. Yeah. Sindhuja, did you get this number?
I got 2034.77.
Oh, okay. So what was your exactly V line value? Can you tell me V line?
1418.9.
On for then?
1418.9.
Oh, that is small. It should be 1480.96. So what is your VM value? V max value? Is it 2094 point something?
Yes, Dr. Ali.
Then you divide that by √2. Divide that by √2.
Okay.
If you divide that by √2, then you should be getting 1480.96. I mean, at least the 1480 you should be getting.
Yeah, 1480. Yes, I got it.
Yeah. Then use that number.
Okay, Dr.
Yeah, so then you should be getting close by this one, 2051. Venkat, did you get exact number?
Yeah, yes, sir.
Oh, okay. Amani, did you finally get close to this one or is still much deviated?
I'm still trying to close to that.
Oh, okay. So from your calculator, you directly use the √3 value, whatever you are getting, because √3 is in the denominator. If it is big, then you will get the lower value. But if you use like 1.7, then you are dividing by somewhat higher value, that will cause you much deviation.
Finally, Dr. Ali, I got it too close. I got 2052.
Oh, okay, that is okay. Yeah, I mean, really, this is, if I rounding, then this is 2052 because there is 0.83.
And
So
my
that's
problem here was, it's my numbers. Power factor, I used 0.92, not 0.95. That was my mistake. I'm so sorry to waste your time.
No, that's fine. That is the other problem. Yeah, that's all. Okay, got it.
I'm sorry.
No, that's fine. Okay, so everybody, then oh, so Sindhuja, did you finally get?
Now I got 1950.
The current value?
Yes, Dr. Ali.
So did you not use, so your V RMS, I mean the V line voltage on 480, right? You got that
Yes,
one?
doctor. Yes, yeah.
Then are you not using P equal to root 3 VL
Zero.
IL cosine theta?
Yes, doctor. I'm using that only.
And then cosine theta, you use that 0.95.
Yes, doctor. Yeah, I use that.
And that root 3, if you have used, and voltage value, which voltage value have you used? You have to use the line value 1480.96, that one.
Yeah, I use the same one.
So then it should not be so low.
Yeah.
Can you check once again?
Yeah, sure, doctor.
And then 5 megawatts, so 5 multiplied by 10 to the power 6 watt. And if you have put 0.95 and if you are using calculator, then you should not get so much deviated result. It's almost you are telling the half of the result.
Yeah.
So did you use root 3 or you use the 3?
I'm using root 3.
Yes. So
Yeah, I'm getting 1949.
look, in your numerator, it is 5 megawatt numerator.
Yes, doctor. Yeah.
And then divide by root 3 multiplied by 1480.9 multiplied by 0.96. This should
Yeah.
be in the denominator.
I'm doing the same thing. I don't know where it is.
Maybe then your calculator is not helping you.
Yeah, I guess.
Yeah. You are trying to help, but your calculator is not helping you.
Yeah.
Okay, so therefore,
Okay. I'll check later, doctor.
yeah, you check later. Okay,
Okay.
you have written the equation number correctly, but then that is the calculator issue, I think. Yeah.
Yes. Yeah.
Yes, I have written answer. You check. Okay, so everybody, then moving forward, because we are looking at transient stability enhancement, but energy storage can also improve the transient stability. And if you Google just this keyword, transient stability enhancement by energy storage, then at least you will get 2 examples, like superconducting magnetic energy storage and then supercapacitor energy storage. These two has been widely used for transient stability enhancement, even for the conventional power grid system. So now you know that there is battery energy storage that is frequently used in microgrid. That is different thing. So the goal of the battery energy storage, or there are other types, pumped hydro, hydroelectric, compressed air energy storage. Those work with the wind and then photovoltaic system. But these two energy storage are widely used with the conventional power grid or with the hybrid power grid. So that's why we will be discussing a little bit about transient stability enhancement by energy storage. So therefore, you all know what are the role of energy storage. That, for example, you all know about the function of battery, which comes together with the solar system. So what does it do? It works as a backup power. Like at night, because PV does not produce any power, or even in cloudy moment, because solar cannot produce power, at that time, the stored energy in the battery is used as your backup power. So that is the common thing, you know. But there are two more additional point. Of course, on that we are concentrating in this class, transient stability improvement that we'll be looking. In addition, the energy storage can mitigate power frequency and voltage fluctuation resulting from those power sources like solar or the wind system. So that's why any energy storage, whatever this is, this on superconducting magnetic type or supercapacitor or any other type, they basically serve these 3 purposes: backup power, mitigation or suppression of or reducing power frequency voltage fluctuation, and transient stability improvement. So therefore, we will be concentrating on this on transient stability improvement. Now, therefore, first of all, these two, I mean, you remember those who joined that modern grid or renewable class, we discussed these things extensively. But here for this class, for transient stability improvement purpose, we will be using these two. So here you see that superconducting magnetic energy storage, that will be the structure. That will be the structure. And this structure you will be installing at the generator terminal. Like everybody, think about that braking resistor that we covered like several classes back. Braking resistor was connected at the terminal of the generator in parallel. Similarly, this will be a parallel connected device. Can you see here I have written 3-phase AC from generator terminal bus. Exactly at the generator terminal, you will be connecting these 3 points, FH, BH, CH. And then including this transformer until this coil, superconducting magnetic energy storage coil, which is called this one, this superconducting magnetic energy storage. This means this technique will store energy in the form of magnetic field across a coil. So this is a coil, it looks like inductor, but this will hold the energy. This will store the energy, and when there is fault or disturbance in the system, then we will be utilizing this on to maintain the stability. That is the goal of this structure. So that's a whole thing. Now everybody see the whole thing is called that SMS unit, superconducting magnetic energy storage unit. So what are the components that you need to look? First, there is a Y delta connected transformer, and of course step down. So for example, this is one example. If the grid voltage, generator terminal voltage here is 66, then it is reducing. It is step down 2 kV, because there are power electronics device, so they have some withstanding capability. So you have to convert in such a voltage that is tolerable for this power electronic device. And you see here is that coil. So now you can argue that why is this arrangement? What's wrong with directly connecting this coil with this one, with delta connected system? Then the first question is, if you directly connect here with this coil, then that will be the AC power. Everybody say, you assume that you don't have these things in between this power electron. It is directly connected to AC. Therefore, there will be power flow. There is no problem with that, but it cannot hold any energy. It cannot store any energy. You know that to store energy, to hold the energy, there should be DC here. You must need the DC. We showed the equation like half CV square in case of capacitor, or for inductor, half Li square energy stored across a coil. Those are like DC. Those equations are applicable for DC. In AC, you can use the equation, but because AC is sinusoidal, there is positive peak, there is negative peak. In on peak, they will store energy. On the negative peak, they will release the energy. So they cannot store because resultant average is 0. With AC it will work, but you cannot store. Consequently, when there is fault on the connected system, immediately it cannot provide energy. So the goal of this one, because we are looking transient stability improvement, therefore the goal is that this will have some stored energy. Already there is stored energy, that is the assumption. And once there is fault in the system, because during fault power will go low, voltage will go low, this energy storage will support voltage in this direction. So that's why, so everybody say, because I said it should be the DC here, not AC, that's why first this is the AC, clearly this is the AC, because this is transformer output. With the help of this one, voltage source converter using IGBT. IGBT stands for insulated gate bipolar transistor. That is first converted into DC. This means that, can you see that there are diode 1, 2, 3, 4, 5, 6. So 6 pulse rectifier. So they are converting into DC. And here you got the DC. And again, as we are discussing in case of PMSG based wind generator, this capacitor will hold or maintain a constant voltage here. And you got DC voltage here, which is needed by the SMS coil. But then you need to control that voltage. That's why there is DC to DC chopper circuit. I mean DC to DC conversion. Again, that uses IGBT. There are two IGBT and these two are the diode. So this is the direction. When it is charging, then this is the flow. And when it is discharging, then this is the direction. So therefore, during charging mode, when the coil will consume power from the grid, then this device and this device will work. Those two will be turned on. And if you need to send power from the coil to the grid system, then this and this will work. This will be the direction. In that way, this stores the energy. And you see, as I said, because this is the DC, clearly you understand that this is DC. So of course, this whole zone is the DC. So therefore, its current multiplied by the voltage, that is its power. Therefore, here the power is DC. But then when it is sending power after the transformer, it is AC. Or when it is sending power in this direction, it is AC, but ultimately it is DC. So therefore, in other words, SMS coil or supercapacitor, if it is capacitor, then supercapacitor energy storage, they control the DC power here actually. So now, and then here you see there are IGBT, those rectifier uses during rectification mode when converts AC to DC. And then when you need to send power from this coil to this side, then as I said, these two will work, and then these 6 IGBT will work. And they will convert from DC into AC. So therefore, these rectifiers are for AC to DC, and these 6 IGBTs are to convert DC into AC. So this, in other words, this SML coil is your bidirectional. So therefore, I think Lakshmi these days, I guess you are studying this voltage source converter, right? Yeah.
Yes, Dr. Ali.
Yeah. So therefore, your voltage source converter is bidirectional with the photovoltaic system. So this combination of parallel combination of diode and IGBT makes it bidirectional. Therefore, as I said, in this case, these are converting into DC, and then these 6 IGBT are converting DC into AC. In that way, it is bidirectional. Therefore, when you are dealing with a smart inverter for PV or a smart inverter for wind system, you must need this type of arrangement. So it is bidirectional. So therefore, in this case, so therefore everybody, you note down or you take a picture of this one, because soon we will be solving some numerical problem based on this diagram. So therefore, keep in mind, if it is a capacitor here, supercapacitor means very big value of capacitor, then you can call the device as supercapacitor energy storage system, SES. And when we are dealing with the coil, it is called superconductive magnetic energy storage. It is called superconductive because by force, like you remember that superconducting fault current limiter, we were maintaining the superconductivity with the help of a refrigerator so that the resistance value becomes 0. Here also in real practice, you need a refrigerator. So here I am just showing coil, but superconducting, meaning that during normal condition, there will not be any energy loss. It will hold the energy by half Li square. How much current is flowing? What is the value of the L, inductance value, and half Li square. That is the equation. So during normal condition, it is the expectation that there is no loss, resistive loss. Therefore, there is a refrigerator in real practice, and that is continuously making it cool down. So, and then you see that what is the benefit, although the power electronics involved, but it works very fast. So here I have written some of the feature, you see, salient features of this unit: fast response. It can charge or discharge in megajoule of power in millisecond, like in 1 millisecond, 2 millisecond. Quickly it can consume power in this direction, or it can deliver power in this direction. So that is the meaning fast response. High efficiency, charge discharge efficiency over 95%, and ability to control both active and reactive parts. These three are the features of both this one as well as that supercapacitor energy storage system. And that is the reason. Because of this reason, we will be using this to energy storage device for transient stability enhancement, especially the last one, ability to control both active and reactive parts. So therefore, as you can see clearly, we discussed that because this portion is DC, so therefore this will control the power, and once DC is converted into AC, that corresponds to that active power. And here I have written one thing, and like how it controls the reactive power. Everybody see, excluding the DC to DC chopper and SMS coil, the remaining portion constitutes the STATCOM. So meaning that in this configuration, if you delete this portion, if you assume that there is no coil and there is no this circuit, you have only this capacitor, then the remaining portion, the left side is starting from here, left portion is the STATCOM. So here I have that, I think before once I showed you, this is STATCOM structure. In the, look the top one, there is capacitor and that VSC, voltage source converter, and that transformer, step down transformer. This constitutes, or this forms the STATCOM. And bottom portion is that STATCOM controller, how it works. So therefore, excluding this thing, the DC to DC chopper and SMS coil, the remaining portion is the STATCOM. And you know that STATCOM controls the reactive power. So this means the whole arrangement, the whole system controls both active power and reactive power. That is the meaning of this. So its feature is it has the capability to control both real and reactive power, and which is needed actually to maintain the transient stability. That is the reason we are choosing this SMS coil or the energy storage system to maintain the transient stability. So therefore, when it is SMS unit or SMS energy storage system, you will keep in mind that you need this whole arrangement. You have to keep in mind that you have Y delta transformer, and then you have voltage source converter, DC link, and then chopper circuit, as well as the coil. The same thing if it is supercapacitor energy storage, there is everything there. Here it is the very high value of capacitor. Accordingly, it is called the supercapacitor. There's the thing. So therefore, we will be solving some problem. So therefore, if you see this structure, here it is AC, then this is simply the transformer. Here you will get step down voltage, whatever it depends on number of turns or what value will be given in the problem. And then you see this portion is AC. So you know the equation that VDC 3 Vm by pi cosine of alpha. Then you will get the DC here. Or if you know the DC here, with the using same equation, you can convert back into AC. And then here I said for the SMS coil, everybody listen carefully, for the SMS coil, if you know the current here, or if you know what is the voltage here, then if you multiply voltage by current, P equal to VI, that is its power. So you don't need to think about the cos theta. It is not like P equal to VI cos theta. There is no cos theta here. You see, clearly this portion is the DC. So there is no question of any reactive power or any active power. So there is no cos theta or sin theta. So therefore, power will be simply multiplication of voltage and current, P equal to VI. And the energy storage will be half Li square. In case of capacitor, half CV square. And now you see this portion for the DC to DC chopper. So probably you remember before once we discussed during DC to DC chopper based braking register, it is related with the duty cycle. So this means if you know the voltage here, which is VDC, then voltage here will be duty cycle multiplied by the input voltage. So therefore now you can note down that output voltage of the DC to DC chopper is the duty cycle multiplied by the input voltage here. These are all conversion you need to solve the problem about the SMS coil or the supercapacitor energy storage system. So everybody, could you follow me?
Yes, Dr.
Yes, sir.
Yes. I think in the modern read class we discussed these things. Lakshmi and Sindhuja, could you follow me?
Yes, Dr. Ali.
Yes, Dr. Ali.
Yes. So this is therefore now, and then now we can take a even picture of this one. This just take a picture even on your cell phone. Although these will be like uploaded and you will be looking video, but it will help you to solve the problem. Just take this picture. So this the whole thing is the energy storage system. So now based on that, now I would recommend you, like if you Google, I myself have a couple of publications with that SMS system. Like, can you see this one? M. Charlie, that is my name. And J. Tamura, he was my advising professor. Yeah. And then I published this one in 2010 when I was a postdoc fellow in Canada. Can you see the transient stability enhancement by fuzzy logic control SMS, considering coordination with optimal reclosing of circuit breakers? So I published IEEE transaction power system. So if you just Google, and then I recommend you all like download this one and read. I recommend you to all of these 5. Like I am the author in all of these. First 3, like I am the first author, and then number 4, 5, like I am working with the students later, and like I am just as a co-author. So number 2, that SMS system is used for transient stability improvement of wind generator. It is like IEEE transaction or industry application. And then this on IEEE transaction control system, we published 2007. Again, fuzzy logic control, SMS for transient stability augmentation. So this paper, number 3 and number 1, like pure conventional system. Number 2 is about the wind generator. And then number 4, both hybrid system, I mean conventional system plus wind farm. And then number 5, again, the conventional synchronous machine-based system. It is about the supercapacitor energy storage. So therefore, number 4, number 5 about supercapacitor energy storage. And then top 3 is about SMS. So I would recommend you all, you download. So this slide is available here. As long as you are using university credential, you can download these papers. And then please read. So then you will get much more information. Okay, so then moving forward. So now we will solve some problem. Oh, actually the picture is here. So although I told you to take a picture, but actually it is here, so you're fine. Everybody read the problem. In order to improve the transient stability of the synchronous generator shown in figure 1, this is a power network, figure 1. There is a synchronous generator. It is providing power to the grid or the infinity bus with the help of a transformer and then double circuit transmission line. This represents 3-phase system. So there are double 3-phase system. And an SMS shown in figure 2 is used. So meaning that, you see, I have shown that K is the fault point for this system. This system was running fine, and suddenly there is a fault at this point. And to improve the transient stability, you are using this configuration, which I was discussing a few minutes back, this one. This means that, this 3 terminal, this 3 point will be connected actually here. it will be connected at the grid point, at this point. Then that can handle the fault. That is the meaning. So now read the problem. If the power and energy rating of the SMS coil is 5 megawatt and 10 megajoule respectively, this means that this coil here, it has the rating of 5 megawatt and it has the energy storage capacity 10 megajoule. Then what would be the number of turns required in the SMS coil of 2 Henry in order to produce a flux of 100 Weber? Now you see, because this is a coil, and as I said that DC current is flowing. So what is the consequence of flowing current? If any current flows through any coil, then it will produce flux. So it says that it will produce flux of 100 Weber. And the L value is given, inductance value is 20. Also, what would be the voltage across the SMS coil? What is the voltage here? That's the question. What should be the voltage here? So what voltage is available here? That will make this amount, like 5 megawatt and 10 megajoule. So everybody, do you understand?
Yes.
Yes, Dr. Ali.
Yes, Dr. Ali.
Yes, please start solving. So, okay, one thing you need for this one, what would be the number of turns required in the SMS coil of 2 Henry? So let me just for a moment, let me take you to that whiteboard and write down the equation, and then I'm coming back. Let me clean off these things. Okay, so everybody see, you have a coil, it has the value L, and you see that I'm twisting, meaning that those are called the number of turns N. This is one turn, and then when I'm twisting, number of turn 2, then number of turn 3. That is the meaning. So therefore N is the number of turn, and so the current flowing, which is I. And you know what is the property of current flowing through a coil? It will produce flux. So this is the amount of flux, phi. So the relationship among these four quantities, this is the relationship. What is the inductance value? Ln phi over I. This means actually inductance is the rate of change of flux with respect to current. That is the meaning. So therefore, everybody write down this equation. In case of coil, when current flowing is I, it has number of turns N, and it is producing flux phi, then this is the relationship. L equal to N phi over I. So please all note down this equation. So where L is in Henry, I is in ampere, N is just number of turns, phi is in Weber. This phi is in Weber. Everybody, could you follow me?
Yes, Dr. Ali. I got 200 for number of turns.
Oh, okay. So have you all written down this one?
Yes, Dr. Ali.
Okay, very good. So now I am going back to that problem. Okay. So now see this one. Now look that information and you need to use that equation to get the number. So Amani, you said number of turns 200. That's right. That's right. And I think there is the second part also. What would be the voltage across the SMS coil? There are two questions. So therefore, let me write down the answer here. Answer here. Number of turns and value is 200, and B should be 5 kV. I mean 5000 volt. So everybody see there are two questions. So if the power and energy rating of this SMS coil is 5 mega or 10 megajoule respectively, then what should be the number of turns here? That is one question, provided that the inductance value is 20 and flux value is 100 Weber. Also, what should be the voltage across the SMS coil? What is the voltage that appears across this one? So as I said, like I got 5000 volt. So Manoj, Kamana, so
Yes, Dr. Ali, I got 200 turns for the N value and I'm on voltage calculation.
okay, please keep going. So Amani?
Yes, Dr. Ali, I got 5,000.
Okay, great.
Mhm.
Yeah, I got 200 turns, sir.
Okay, and then now go for the voltage calculation.
Yeah, voltage. Yeah. Yes.
Okay. So therefore, Lakshmi and Sindhuja, you see this 5 megawatt is for this coil, for the SMS coil. So this means 5 megawatt is the power rating. So 5 megawatt is the multiplication of voltage and current. Simply the multiplication of voltage and current here. That then you can say that is 5 megawatt. This means if you know what is the magnitude of current here, then you can calculate the voltage. And you can use this information 10 megajoule here. What is the energy storage equation? Half Li square. Half Li square for the inductor. So then see the inductance value is given 20 and energy value is given. So from there you can calculate how much current is flowing through the coil. You are getting the I. So if you know what is the I and if 5 megawatt is the power consumption, then you can find out voltage. So Lakshmi?
Dr. Ali, I got 5,000.
Okay, great. Yes. Sindhuja, did you get the first result? Number of turns?
Yes, yes, Dr. Ali, I got N is equal to 200 and I'm working on the voltage.
Okay. For voltage, as I said, like that 5 megawatt, it is the capacity here. So that is V multiplied by I.
Okay, Dr.
Yes.
Dr. Ali, I have a question.
Okay.
So why we are just using B multiplied by I for the real power here?
No, that
For
is
five.
here that I said here you cannot say that is the real power. That is the DC power here.
DC, yeah. I got it. I'm sorry.
Yeah, and that is the reason we are using P equal to VI.
Okay, I got it. I got the 5.
No, I understand. No, you're fully fine. Like P, if you say, okay, of course this is not three-phase system, right? So by looking
Yes,
at the
yes.
coil, even if you say that this is single phase and you say, okay, P equal to VI cos theta, but if you see that is also wrong because this portion is fully DC.
Exactly.
Yeah. Meaning that cos theta value is 1. Yeah.
Yes.
So that is the key, SMS coil, you need the AC here. Sorry, you need the DC here.
Mm-hmm.
That is at the big think, Manoj, think about your cell phone charger. What is in your cell phone charger or your laptop charger?
DC.
Yes, right. You plug in AC and then there is rectifier
Mm-hmm.
adapter. Because only that, because your cell phone needs to hold energy, your laptop needs to hold energy. You need to convert into DC. That's the same concept here.
Exactly.
Yes. Now you can argue that no, I will not store energy here. I will just keep a blank empty coil here. Whenever I need to send power, it will be charged, and when I need it will discharge. So think there is no problem for the charging. If the coil is empty, then you can send and it will charge. but you need to compensate power. Suddenly you need to send some power from here to here. If it is empty, empty means if there is no charge, and how you will send power. So that's why that is the necessity of having some amount of charge always here, whether it is whether it is operating or not operating. That which is called standby mode. That standby mode is like half Li square that will hold energy. See, like you made 100% charge on your cell phone. You are holding. Why you made the charge? Because anytime you may need to use your cell phone, you may need to talk, right? Yeah.
Yes.
If it is empty, how can you receive or how can you talk? The same meaning.
Exactly.
Yeah. And because you need to hold the energy for uncertain future use, you don't know that when what will happen and when this will start working. That's why, irrespective of the fault, it is always connected, this 3 terminal here, and it is always maintaining some charge. And because it needs to maintain some charge always, that's why that refrigerator question is coming. Now we can argue, no, I will not be using refrigerator. But if you don't use refrigerator, because continuously it will hold energy, half Li square, but then this coil will be heated up and it will produce some resistance, and that resistance will cause some loss. And meaning that within a few minutes, the charge will be empty. That's why you have to hold the constant current here, because main thing, half Li square. Therefore, your coil is there, but you have to maintain a steady current. You have to maintain a DC current. That's how you need to maintain, to provide the R value 0. And accordingly, the name goes superconducting. And you must need a refrigerator or cooling medium. I mean, in real practice, in addition to that refrigerator, there is liquid helium and liquid nitrogen into which this coil is immersed. Do you understand, Manoj? Yeah.
Exactly. Yes.
Yeah. In real practice, this coil is put into the liquid helium or liquid nitrogen just to keep it cool down. Plus, in addition, you need the refrigerator.
Yes.
Yes. That is the principle.
Thank you, Dr. Ali.
Yeah. That's why I mean, this rating is, it looks like this power megawatt real power. Yes, I mean, real power in 3-phase system, single phase system, even DC system, power is expressed in that way. But in this case, this 5 megawatt is the DC power. Once it cross this on, this component here, then that is the real power. So therefore, for example, you have a 10 megajoule capacity charge and you send some power in this direction. Once it comes in this zone, then that became the real power. That is the thing. The same thing, you are sending some power from the grid. Of course, that is the AC power. Once it came in this area, I mean, across the DC link, then that became the DC power. So this just the power conversion. I mean, it is maintaining law of conservation of energy. Here it is DC. You are getting equivalent real power here. The same thing. It is here AC power, but then it is equivalent DC power here. That is, I mean, properly the law of energy of conservation is being maintained.
So as it stores the energy, it will lose the supermagnetic things like supermagnetic energy storage.
Yes. It will lose, and to maintain that, you need that refrigerator.
Yes, Dr. Ali.
Yes. Now, and also to answer your question more appropriately, now over the time, let's say 10 years, 15 years later, this coil might be damaged, for example. Then you might need to replace that coil. That even though your refrigerator, you are putting it into liquid helium nitrogen, but it looks like it is not working properly. Like it is generating some heat or something. There is some loss. Think that sometimes your like laptop battery or then cell phone charger does not work properly, or like quickly you are losing the charge from your cell phone because of the battery, because of some issue. So there can be any leakage or something, like leakage current flowing, and that's why your cell phone is not keeping the charge or laptop is not holding the charge. Same thing here. I mean, over the years, the magnetism or the property of this coil may be damaged, may be broken. So you might need to replace. So we are assuming that no, it is a properly good coil, superconductive coil, but to maintain the resistance value 0, you must need a refrigerator, and also you have to immerse it inside the liquid helium or nitrogen. Those work as the coolant, helium or nitrogen. Okay, everybody, did you get these results, everybody?
Yes, Dr. Ali.
Yes, sir.
Yes,
Okay.
Dr. Ali.
Okay. So then fine. Okay, then again, moving forward, there are a few more problems. Okay, just everybody read number 1, and then I think we don't have much time today. Just read this one. Find out the power rating of a voltage source converter-based superconducting coil energy storage system used to maintain transient stability of a 3-phase synchronous generator supplying power to a grid. The transformer of the storage unit has a turn ratio of 2:1, and the primary side voltage is 2100 volt. The chopper duty cycle is 0.85. While the inductance value and energy rating of the storage coil is 2 Henry and 10 megajoule respectively, and the firing angle of the rectifier of the SMS unit is 30 degrees. So therefore, if you see this on, question is find out the power rating of the voltage source converter with SMS coil system. So this means that again you have a similar configuration. Everybody think that this is your total configuration. And in this configuration, you are asked here, what should be the power value here? Like for example, in this problem, power value was given 5 megawatt. That is not given, and that is the question. What is the power rating here? That's the question, power rating. And its Henry value is given 2 Henry. Energy storage capacity 10 megajoule is given. Firing angle of the rectifier is given. Chopper duty cycle is given. So as I said, how we will use the chopper duty cycle? Here you will be using chopper duty cycle. Like voltage here, output voltage here is voltage here multiplied by the duty cycle. In other words, duty cycle is output voltage divided by the input voltage. The voltage, this DC voltage here, that is your input. And the voltage across the SMS coil is your output voltage. So chopper duty cycle D is output by input. Keep in mind. So therefore, that is that information, 0.85. And for the transformer, see, transformer of the storage unit has a turn ratio 2:1. Primary side voltage is this one. So therefore, for this transformer, this side voltage is 2100. And turn ratio is given this side 2, this side 1. So therefore, here the voltage will be half. So meaning that 1050, 1050, because of this turn ratio. Using this information, I think now everybody can find out the power rating. Everybody, do you understand?
Yes, Dr. Ali.
Yes. So you just keep going. I mean, I'm releasing you. You should be trying this on, and you let me know that what result you are getting in next class. So everybody just try this on at home. You complete. Okay, with that, I think today I like to conclude. So, do you have any questions, comments, anybody? Is everybody fine?
Yes, Dr.
Yes,
Ali.
Dr. Ali.
Yes, sir.
Okay, so therefore you complete number 2 at home, and then in next class you let me know what result you get this one.
Okay,
Okay.
Dr. Ali.
Okay, so with that, like I will stop sharing.